Hi, and welcome to the ninth lecture in my series on Introduction to Quantum Theory and Technologies. So, in the last two lectures, we did two different types of topics. The first one, which we did in lecture 7, was how quantum measurements work, so how measurements work in quantum mechanics. And we learnt there that inherently there's a probabilistic aspect of measurements in quantum mechanics. And in lecture 8, we talked about how we can represent quantum states using different bases. So you can represent a quantum state in, you know, one basis, but you can represent the same quantum state in a different basis. So we can actually combine these two ideas into a more general type of measurement, and this is basically what we're going to be talking about in this lecture. So it's measurements in other bases, and so previously I had this kind of schematic picture of what is a kind of a measurement device in quantum mechanics, and so some particle goes in here, and it's measured randomly, and there's some outcome of the measurement, right? And before, what we didn't have is this little knob that I've just sort of drawn on the top here, and this actually is something which means you can actually, measurement is not like there's only one type of measurement, there's actually all kinds of different measurements that you can do, and it's like a variable knob that you can sort of twiddle on the measurement device that you can change the type of measurement. So this is what we're going to be talking about this lecture. Okay. So let's just recap a little bit about how measurements work. So this is what we already talked about in the previous lectures. So in lecture 7. So if we have like a quantum state here with some superposition of 0 and 1, what we learnt there is that we stick it into the measurement apparatus, that device that I showed you on the previous slide, and then randomly it will turn into either 0 or 1. And the probabilities of those measurements are just given by the modulus squared of each of the coefficients of these 0 and 1 states, right? I also showed you another way of actually writing or working out how measurements work in quantum mechanics. And so if we have the two measurement outcomes of 0 and 1, we can firstly write the probability in terms of this one. So if we wanted to work out the probability of the state turning into 0, as in, this outcome here, then we would just work out this quantity here, and essentially you apply this operator to that state, and then take the norm of the resulting vector, and then that gives you that probability. And also, we can also work out what the outcome of the state is. Again, if we multiply the measurement operator by the state, and then we have to divide by the square root of the probability, then we get what the measurement outcome is. In fact, you always just get the measurement outcome of whatever state that you're talking about in this case. So the outcome, it would be just be 0 or 1. So that's how measurements worked. So that's what we already know. So we're going to, as I said, combine this idea with basis rotation. So in fact, we don't really have to always be measuring 0 and 1. Actually, we can equally measure any pair of states so that they are orthogonal. So this 0, 1 is actually just one example of a type of measurement that we can make. We can equally measure in, say, a pair of states here, which I'm called S0 and S1. So, some random name for these two states. So state 0, state 1. And we learned in the last lecture that we can always write a kind of a pair of orthogonal states in this way. So C and D are some coefficients, and they're normalized. I didn't write it here, but so these are of course normalized in the usual way. So C squared plus D squared. You need to be choosing it so that it's equal to 1. Then we can always find the state which is orthogonal to that state by just kind of flipping the two coefficients, taking the complex conjugate, and then putting a minus sign. So that pair of states is always orthogonal. Okay, so that means that if we write the state in terms of S0 and S1, and we can always do this, we can always rewrite any kind of state in terms of some pair of orthogonal bases. So it's basically like, we've got our vector here, and it's it's pointing in some direction here, and so we could represent that blue vector there in terms of 0 and 1, but we could also equally represent it in terms of S1 and S0. Right? So then, assuming we could write it in that form, so A and B, then the measurements just proceed in exactly the same way as we're already used to. So we've got our state, we've rewritten it in terms of the S0 and S1. We stick it into our measurement apparatus, which is going to be measuring our S0 or S1. Then what happens is very similar to what I told you before, which is that the probabilities of these outcomes are just equal to the modulus squared of the coefficients here. So the coefficient, the outcome of getting S0 is just mod squared A, and the outcome is just S0 itself. Same with S1, the probability is mod B squared, and the outcome is S1. So, so we can actually just do the same kind of thing as we've already done, but we need to, of course, first write it in this form in order to work out what these probabilities are. Okay, so let's just do a kind of a quick example so you can get the feel of it. So previously in lecture 8, what we did was we started with some state like this. This is some arbitrary state. Again, these alpha and betas are normalized. I've got to write it here, but alpha and beta squared, alpha squared, beta squared, modulus are all normalized. And so we could write this same state in terms of this so-called plus and minus basis. And I won't go through the steps again because I already did it, but you can write it in terms of these in this form for this basis. Okay. So in this case, what's going to happen is, so we start off with the same state, which in the 0, 1 basis, it's equal to this. Then we stick it into our measurement apparatus, which this time is going to be measuring in the plus minus basis, right? Not the 0, 1 basis. So what happens is that we get two outcomes, plus and minus, and the probabilities are the modulus squared of the coefficients of plus and minus. Okay, so this is where you have to be careful. It's not these coefficients, not the alpha squared, it's alpha plus beta over square root of 2, because that's the coefficient of plus. And because we're measuring in the plus minus basis, we need to be looking at the coefficient of the plus and minus states. Okay, so that's the probability of getting that plus state, and this is the probability of getting the minus state. Okay, so it's alpha plus beta mod squared divided by 2, or alpha minus beta squared mod squared divided by 2. Right. Okay, so we can, so in a way that's pretty much the main message of this lecture actually. So that's the most important fact to get from this lecture. I'm just going to also tell you a little bit about other ways to calculate it, and sort of various facts which result from the fact that you can do these more generalized measurements for the rest of the lecture. Okay, so just like before, when we were covering measurements, we can actually figure out what the probabilities and the final state is just by basically reading off the state. So we just first like rearrange the state or just rewrite the state so that it's in this form, and then we just simply like read off the probabilities just by looking at this. That's sort of like method number one, right? Method number two is using the more sort of mathematical way of doing it, which is using measurement operators. And what I want to show you here is that you can get exactly the same results just by using the measurement operators. You can basically just figure out exactly the same thing. And sometimes it's sort of easier to do it this way, or sometimes you want to do some kind of more general calculation, and sometimes it's better to do it this way. For the simple example that I showed you, maybe the way that I did it on the previous slide is good enough. But handy to know a kind of second way of calculating. Okay, so as we said before, how do you work with the measurement operators? Well, we first write down these operators, measurement operators. So that's say M0, M1. So M0 and 1 are just some, again, orthogonal states. So I haven't told you what they are yet, but you can choose them as you want. And then the probabilities, as we said before, you apply the measurement operator to the state, then you take the norm of that state. So that gives you the probability, and then the state after measurement is this, right? So we basically just use that technique for this example. So let's just do this example. Same example as I did before, but just using more this measurement operator method. So we've got our state alpha 0 plus beta 1. And suppose we wanted to work out what the outcome of the probability of getting the plus outcome is when we do that plus measurement. Okay, so in this case, maybe the advantage of the measurement operator method here is that you don't have to like rewrite the state in the plus minus basis. So before, when we were doing the sort of method one, we had to kind of rewrite this state here, right? The measurement operator method, you don't have to do that. So it's probably about the same amount of work depending on how you do it. Okay, so let me just show you that you can indeed work it out and indeed get the same answer. Our measurement operator is this plus plus, this outer product of the plus. Probability, as usual, is this norm of the thing M0 applied to the state. Okay, so let's work out this thing. What is M0 times psi? Well, okay, so here's M0, here's that state psi, so that's that guy there. Yeah. Okay, then we multiply this operator by this state, and this is always true of any kind of quantum mechanical calculation. Anytime you see this conjugate vector and then the regular vector, so anytime you see this kind of angular bracket structure, you can basically slam them together and take the inner product, and that becomes a number. Okay, so this plus hits this vector here, and then you slam them together, and then you get this inner product of plus and 0. This vector with this 1, slam them together, you get plus and 1. Okay, and so all this stuff in the brackets here, this is just some number now. Okay, so it's important to distinguish between like what's a number, what's a vector, what's a conjugate vector. But once you've taken the inner product, it's always a number, right? It's just a number. Alpha is just a number. Plus and the 1 inner product is also just number, beta is number. So obviously this stuff here is just a number. It's a complex number, but it's just a number, right? and the only vector that you get left over is this plus here. Okay. All right. So now we need to work out what this number is. So let's first work out what is plus in a product with 0. Okay. So just from the definition of plus, so we just put in the definition. Okay, and here's 0 plus 1 conjugate vector in a product with 0. And as usual, this 0 in a product with itself is equal to 1. And the 1 in a product with 0 is, these are orthogonal vectors. So remember, these form a kind of a right angle. So the inner product of those is 0. So in other words, this term just disappears. This term is just 1, so you just get 1 over square root of 2. Right? For this one, inner product of plus with 1, same kind of calculation, except that this term is going to be 0 because this inner product here with the 0 and the 1, they're orthogonal. That becomes 0. Inner product of 1 and 1 is just 1, and then you get 1 over root 2. Right. Okay, so now we can work out what the state is after the application of M0. So, so we've got that thing there, which I just copied from the previous page. Both of these inner products they were 1 over square root of 2. So the new state is alpha plus beta over square root of 2. Okay. So I mean, sorry, I'm not saying the new state after the measurement. I mean this new state after just of whatever this quantity here is, m0 times psi. This is the resultant of that. Okay, and then from there you work out the probability. Just here we've got this one, and then you need to work out what the conjugate vector of that is. Conjugate vector, you always just basically, if you start with a vector, then you just flip it the other way. And any coefficients, you have to take the complex conjugate. Okay, so here's the complex conjugate of that number, and this term is just coming from the regular right-hand side, this vector here, and here we've got the our inner product, sorry, of plus, and this thing is always just 1. So it's just these two things, and a more compact way to write the same thing is that. Okay, and that's the probability, and notice that that is exactly the same number as what we got here, right? So it gives the same probability. What is the measured state? So let's just check that it gives the same result for the measured state. So we take what we've got here, divide by the square root of the probability, which we just worked out a moment ago. So it's that thing here from here, and square root of that thing which is there, and just you can see that this is the same number, except that this has got the modulus, and this doesn't have the modulus. So whatever this complex number here is, so just imagine that this thing was some complex number with modulus er to the I, let's say phi or something. So on the complex plane, this is some number that's sort of out here somewhere. Here's the real axis, here's the imaginary axis. Then this modulus is just the r, right? So you just get left over with this phase. So this is why I've written it's proportional to that, because okay, I could have equally written this as e to the I phi of plus, and you get this sort of phase factor. But as I explained in one of the previous lectures, these global phase factors never really do anything in quantum mechanics, so that's why it's not very important. So often people just kind of drop it. Okay. But anyway, the important fact is that apart from this e to the I phi, you get exactly this state plus, which also agrees with the outcome here. So this thing here. So the outcome is plus, as we had before. up to some phase according to the measurement operator method. And everything basically agrees with the previous methods, right? Okay. So by the way, in whatever we are going to do here, actually the final state is always just the state that you are measuring. So, it's kind of an obvious statement that I've got some quantum state, and I'm going to be like, I'm going to measure whether it's like state A or state B, and then say I find that it's state A, then of course the state that I get at the end is state A, right? So that's basically what this is saying. So I've basically done a measurement. I wanted to check whether it's plus or minus. I found that it's plus, so the state is plus, right? That's basically all this is really saying. So this is, sometimes the mathematics gives you sort of obvious kind of results, if you like. So yeah, so that's basically what we have there. Okay, so and then get on to slightly different, well, an application of basically what we've been talking about here. So, what in the classical case, because we take measurements for granted, we don't really think too much of concepts like distinguishing between states, right? So, for example, if I had a series of these are like counters, like checkers or something, and one side is red and one side is yellow, right? So if somebody is giving me like a stream of these um, counters and they're either red or yellow, classically, I kind of take it for granted that I will be able to tell that it's red or yellow, unless somebody's blocking me from seeing the counters or something. I mean, assuming I have the counters there in my hand, I assume that I will be able to tell the difference between the two sides. So, work out, okay, is this one red or is this one yellow, right? Okay, so it's just such a non-problem in classical physics that it doesn't really have even a kind of a good name, right? Turns out in quantum physics, it's actually not possible always to distinguish between two states. So if somebody gives you two different states and you say, okay, can you please tell me which is which? So I know that this is in state A and this is in state B. Can you now do some kind of measurement and work out, which is which? Then the answer is that you can't actually always, like with certainty, work out which state is which. And so that's like kind of a peculiar aspect of quantum mechanics, and it really comes down to the fact that there are, there's like randomness in the measurements. So this is basically what I'm going to talk to you about now. So over the next few slides, I'll tell you why and what situations this happens. Okay. So here's our kind of setup here. We've got counters coming in from the left. They're sort of streaming in, and they are, either all red and yellow. And we've got our box here, and the job of the box is to basically sort the thing out into reds and yellows, right? Okay. So we can write this in a kind of a pseudo quantum mechanical way. So let's call this the case when the counter is red. We can call that state 0, and we can call state 1 when the counter is on this yellow side, right? Okay, so in this case, what we can do is just simply set our measurement device to the basis of 0, 1. And then in this case, because if it's state 0, then with 100% chance we will get the outcome 0. So that means we can perfectly distinguish between this 0 and 1. Okay, so as long as, this box is not broken, and we can do this kind of ideal measurement, we can always distinguish between the two cases with 100% success probability, right? Okay, so now let's make this a little bit more quantum. And one way we can do this is by introducing superposition into the particles that we are sending into our detector here. So in the previous example of the checker pieces, we could only have like red or yellow, and of course we couldn't really have anything like a superposition of red and yellow because that would mean it's in both states at the same time. But of course, with something like an atom, you can be in a superposition, or at least that's what quantum mechanics tells us. So for example, we could send a series of atoms into a detector instead of the checkers, and what we could have are these atoms being in two different types of states. Say these blue ones are in this, say, plus superposition, which is defined in the usual way that I usually define it. So the plus is just the superposition of the two states, like 0 and 1. And here the 0 and 1 are the two levels of the atom. So maybe like 0 is the bottom level and 1 is the higher energy level here. And minus would be the state, basically same thing, except that it's got a minus sign here instead of a plus sign. So otherwise, it's basically the same kind of state, right? So we have two types of superposition states that are coming into this box. So this is actually an example where we can still distinguish between the two types of states with 100% probability, because we have this knob here on the box, which can, you could tune the type of measurement that you are doing, right? So if we didn't have this knob here, then we wouldn't be able to do it, right? But since we have this knob, what we can do is we can change the measurement setting so that it's like plus and in the plus and minus basis. And in this case, as long as we've got it in this measurement setting, then we can distinguish between the plus and minus atoms with 100% probability. And we can show this using the measurement operator method. So, for example, for the plus outcome, and say we're looking at this atom, which is just about to come into the box here. So apply the measurement operator here to the plus atom. Then what happens is, here's our measurement operator, we take the inner product, and what happens is that this thing here is equal to 1, and here's our final state, just plus. We can find what the probability of getting this outcome here is just by taking the inner product of the outcome of this calculation here, this m0 times psi with itself. And so this just becomes plus plus inner product, which is equal to 1. So this means with 100% probability, you can actually find that the outcome is plus if the state is plus. Well, makes sense. If you're curious on finding what the outcome of the minus state is, well, we can work out what that outcome is simply by applying the measurement operator minus minus outer product to the state plus. Now, because this plus and the minus, the inner product of this is actually equal to 0, and you should work out why that is 0 if you haven't done it already, and that is actually equal to 0, so the probability of that is 0. So that means there's basically kind of no sort of false positives. You don't sometimes get minus outcome even if it's plus, right? Okay, so this shows that you can actually still distinguish quantum states perfectly, even with the superpositions. So the story is not so different to what we had with the completely classical case of the checkers, right? Okay, now let's do a case where we cannot distinguish between the quantum states perfectly, right? So in this case, it's sort of like a hybrid of what we were talking about in the last two slides. So now suppose we don't just have all the atoms in 0, 1, nor do we have it just in the plus minus. We've got kind of a mixture of all four of these types of states, right? So we've got pluses, we've got zeros, we've got minuses, we've got ones, and we're going to feed it into this box, but this box only has one knob. We can't just, there is no knob to sort of say, okay, distinguish all four cases. You can either do the measurement setting between 0 and 1, distinguish those guys perfectly, or plus minus. You can't do both at the same time, and this is basically the problem. This is why you cannot distinguish perfectly between such states. So let's sort of see this explicitly. So suppose we have a go with this measurement device on the setting 0, 1. Okay, so let's just see what happens. So of course, with the setting in 0, 1, we can distinguish between these ones which are 1 or 0 perfectly, right? So if it's 1, then with a 100% chance we're going to get 1. With 0, with a 100% chance we're going to get 0, right? But the problem is these other states. We've got these plus minus states. So what's going to happen to those states? Well, for those states, we can work out. For example, let's suppose we had this state here, the plus state come in, and we've still got the measurement setting on 0, 1. In this case, if you perform that measurement there, then what's going to happen is that because the plus state is simply equal to 0 plus 1, then with the probability half, you're going to get 0. And with the probability half, you're going to get 1. And it's kind of 50-50, and you can't really tell which of those states it is. In fact, the answer is it's neither of those states. We're sort of measuring in the wrong basis, if you like. So you can't distinguish between these states. And also, if you, for example, put in the minus state here, so if I change this to, instead of the plus, I put a minus sign here, then I'd still get exactly the same probabilities, right? So these pluses and minuses, they give exactly the same probability distribution, and so I can't tell the difference between them, right? And if I chose, of course, the plus minus settings, this would distinguish between the pluses and the minus perfectly, but then that would actually mess up the settings on the ones and the zeros, and so I couldn't get with probability 1, I couldn't tell the difference between these zeros and ones. In fact, they would give also exactly the same probability distribution. Each of the ones and the zeros would give plus or minus with a 50% probability. So, is there any other smarter choice of basis that we can do? So you might think, okay, fine. So we've got the 1 and the 0, we've got the plus and the minus, and we can sort of visualize it in terms of these vectors as something like, halfway between these guys. The plus is halfway between the 1 and the 0. Maybe, we could have some other basis which is halfway between the plus and the 1 again, and this blue one, which is halfway between 0 and minus, maybe that would do better. And the answer is there's basically no basis that you could possibly choose that you could distinguish between these two states. And you can basically show this by just choosing an arbitrary pair of orthogonal states, and I leave it to you sort of as an exercise, but if you choose this arbitrary basis here, then there's basically there's no angle that you could choose such as to make each of these measurements like 100%. So the aim would be like for a particular, for these four states of 0, 1, plus and minus, what we'd want is to be able to distinguish between those states perfectly, but it's always going to be less than 100%, right? So there's no way to actually distinguish between these four states. So so this is actually kind of how quantum mechanics works. So we've actually kind of hit the limit of what we can actually do with a measurement. And classically, you don't even think about measurements really, because you take it for granted that you can just, if something is in some state, then you can know about it. But in quantum mechanics, this is actually not true. If somebody prepares a state and you don't know what it is, then you can't actually work out exactly what it is with certainty, because quantum mechanics has this probabilistic element to it. So an interesting application of this idea, which we might do later in this course, depending on how much time we have, is actually you can actually perform quantum cryptographic protocols, and there's a famous cryptographic protocol called the BB84 protocol, named after the inventors of the protocol, Bennett and Brassard. They did this in 1984. So they invented a way of actually, sharing some kind of secret key between two parties based on something actually very similar to what I just described in these slides. So roughly how it goes is that you send some 4 different types of states, 1 plus 0, 1, send them kind of randomly, and the person that's receiving tries to measure these states, and the only way that you can measure it is if you actually got the basis of these states correct. So if it's in the 1-0 basis, then you and if you chose that basis correctly, then you could figure out what state it was with certainty. For the other 2 cases, you just get some noise, basically. It's just random. Okay, so then by actually sharing some other public information, so then they kind of the person that's sending the information reveals something about what basis that they were choosing originally, and then eventually they can share a secret key. So I will go over this in more detail later, but the point is that this can be actually used for quantum technological purposes, and this is kind of one of maybe one of the most important applications that we might see in these kind of future technologies based on quantum physics. Okay, so finally in this lecture, I just want to talk a little bit about a related topic, which is quantum tomography. Okay, so the setup is quite simple. So in this case, Alice, who's the person that's sending some state, sending it to Bob, right? But Bob doesn't know what the state is. Right? And as we've kind of discussed before, if Alice only sends one copy of the state and Bob has no idea what the state is, then basically it's absolutely impossible for Bob to work out what that state is, because firstly, he doesn't know what basis to measure it in. So our little knob here on our machine here doesn't know where to set that to. And even if he guessed the basis correctly just by sheer luck, so he just randomly twiddled the knob and he actually managed to get it in the right basis. Where if you get it in the right basis, then you should get it with 100% probability on one of the measurement outcomes. But he'll never know that he got it right because there's not enough statistics to actually work out what probabilities he actually got, because he only did one measurement, one outcome. So say it was outcome 0, then he gets one count in outcome 0, 0 counts in outcome 1, and the total number of measurements was 1. So you can't really estimate probabilities based on that. He might have just been very lucky, or one measurement basically doesn't give you any kind of information, right? Okay, but if Alice sends lots of copies of the same state, then actually Bob can eventually work out what the state is. Okay, and basically this is sort of a kind of a simplified way of actually kind of working it out, and it actually kind of only works if there's only all these states are like perfectly prepared. But suppose Alice has lots of copies of this, right? And they're all exactly in this same state, right? And Bob gets them, say, one by one, something. So what Bob might first do is first he sets his measuring device to measure in this 0, 1 basis, right? Okay. Remember, an arbitrary state can be always written in this form because this is already normalized due to cosine squared plus sine squared is 1. And so if he measures in the 0, 1 basis for this state, then of course the probability of getting 0 is the mod squared of this term here, so that's cosine squared of theta over 2. The probability of getting this term here is just sine squared, and remember this phase always cancels out because we're doing the mod squared. Mod squared always kills this phase, don't have to worry about it. And if we, for example, actually even this we can work out what the angle is. Our task here is to work out what theta is here. But if we've got all these results, we might as well use all these results. So for example, if we just subtract these two, then it becomes cosine squared minus sine squared, and we know that that's cosine of 2 theta, or, well, in this case, it's just theta because we've got the theta on 2. Now just rearrange this equation. So theta is going to be inverse cos of P0 minus P1. Okay, so just from those probabilities, we can work out what the theta is. Okay, so that gives us that theta. What about the phi? Well, we can go and measure in the plus minus basis. So in this case, remember that from lecture 8, we can rewrite any state. If it's originally alpha and beta, then in the plus minus basis, it's like alpha plus beta divided by root 2 is the coefficient of plus, and alpha minus beta divided by root square root 2 is the coefficient of minus. Okay? So we can just apply that formula to the way that we've written the state this time. So in this case, it's cosine of theta over 2 plus this coefficient, e to the I phi sine theta over 2 over square root of 2. So that's the coefficient of the plus. And same thing with a minus sign for the minus. Okay, so I've got a typo here, so that should be minus. Okay, then we can work out the probabilities of these two outcomes just by reading off the coefficients and then taking the mod squared of each of these. So the mod squared is that. And remember, mod squared is just of any number is, C, whatever that number is, times by C star, right? Mod squared is always that. So if we just multiply that whole thing out, I can leave it to you to maybe basically just write out that calculation, but essentially it's like this term multiplied by the same term but with e to the minus I phi, right? So it's like expanding a quadratic, and you'll get two terms of this, so that's that term. You'll get the cross term of this term and this term. You'll get that. This term will be the cross term of this cosine theta over 2 with the complex conjugate, which has a minus sign here. And so you will get this term here. Sorry, there's another typo here. So this term is not there. And finally, we've got the square of this term here. Okay. So we'll get this sine squared theta over 2. That's another typo here. And cosine squared plus sine squared is 1. Got this factor of a half everywhere, so it's that. And here we've got the same factor, cosine theta over 2 sine theta over 2, and e to the I phi plus e to the minus I phi. So remember, e to the I phi plus e to the minus I phi is equal to cosine 2 times cosine of phi. So we've got the cosine of the phi, and 2 sine theta over 2 cos theta over 2 just gives sine theta. We've got the factor of 2 here. Okay, so this one here is basically the same, but we've got minus signs here, so this will be minus signs. And if you add together these two probabilities, they should be always equal to 1, right? Because probabilities always add to 1, so these two terms cancel out and give 1. Okay, so what we can do here to work out what the phi is just simply to rearrange these equations. So we've got whatever these probabilities are from Bob's experiment. And so, for example, if we subtract p plus from p minus, then we'll just cancel out this half, and you'll get cosine phi sine theta. And we already know what theta is from step 1, right? We've already worked that out. So we can just rearrange this for phi. So just put that in the denominator, take the inverse cos, then we can work out what phi is. So basically that tells us how you can work out what Alice's state is, because we've got each of these, basically these two parameters completely determine what this state is. So as I was basically saying, this procedure really only works as long as all the qubits are in exactly the same state. If you have some of the qubits, say in a different state, and this might happen because there's some errors in your the way that you're preparing the states, or whatever reason, maybe even all your states are slightly different. So in this case, our procedure would need to be modified. I won't really go into that for purposes of this course, but just keep in mind that that procedure really only works if they're in so-called pure states, and pure states are basically whenever you have basically all the states that you have in the copies, that they're all perfectly exactly the same. If some of them are slightly different, then this is what you'd call a mixed state, because basically some of the qubits are in different states. It doesn't have to be qubits, any quantum state. If all your copies are not the same, then it would end up being in a mixed state. Okay, so so why is this called tomography? Well, it comes from the fact that, remember, in order to figure out what our state is, we had to actually kind of do two different types of measurements. So we had to do like that 0, 1 basis measurement, and then we had to do that, x plus and minus basis measurement. And so this is kind of reminiscent of what you do in other kind of fields, like so for example, if you're doing a CT scan, like you do in hospitals, if you know how CT scans work, basically CT scan is just like a super, high-tech version of an X-ray, right? So an X-ray, when you take an X-ray, you got your X-rays and they're hitting you, and X-rays are coming in one direction, right? So obviously you just get like a picture, like a 2D picture, right? CT scans work by basically sending X-rays in from all different angles, right? And so you kind of get a picture of yourself from all different angles, and then you stick it into a computer. The computer can figure out basically how this is all working in 3D, how it's all consistent in 3D. And by putting together all these different measurements from different directions, you can actually work out like the full 3D structure of what's happening, say, inside your body. So this is a little bit similar to that. In order to work out what the quantum state is, we can't just do one measurement, because that's sort of only doing a measurement sort of it's kind of only in one direction, right? To work out all the parameters of the state, you need to do a few different directions for a qubit. And if it's a pure state, as I was saying, you could just do two different types of measurements, and then that could work out what the state is. But for, say, mixed states or more complicated states, you need to actually do many more measurements to work out what the state is. So this is why it's called quantum kind of tomography. Okay, so let's just finish off with a kind of simple example of this. So just so that you sort of get the real world kind of feel for this. So for example, let's say Alice sends Bob 2,000 copies of a particular quantum state. Alice has prepared it. She knows what the state is, but Bob does not know what the state is, and he's got his measurement machine, and he's going to work out what the state actually is, right? So he follows the procedure in the previous slide. And so what Bob does is first measure in the 0, 1 basis. So remember, step 1 was to sets his measuring device to the 0, 1 basis, and he can work out the angle just by using this formula here. Okay, so Bob first measures in the 0, 1 basis with 1,000 copies, so he uses 1,000 of these atoms up and gets 352 counts for the state 0 and the remaining in 1. Okay, so we need to work out what this quantity here is. So this is P0 minus P1 inverse cos. So first let's work out what is the probability of getting 0. So obviously in this case it is just going to be equal to 352 divided by 1,000, because we've got 1,000 copies and 352 of those were in the state 0. So the estimate of P0 would be just 0.352. For P1, the probability of getting that one is, well, the remaining counts are all in P1, so it's 1,000 minus 352. And we need to turn that into probability as well, so that's 0.648. So that's that P1. And if we want to work out what the angle is, then we take the inverse cos of P0 minus P1, so that's equal to 0.352 minus 0.648, and so that is 1.87. And I'm working radians here. If you want to turn this into degrees, you can also do that. Okay, and now Bob measures in the plus minus basis, and with the remaining 1,000 copies, remember it's all still the same state, and gets 853 counts in the state plus and the remaining in minus. Okay, so just from our formula a couple of slides ago, our formula for phi is equal to this guy here, so p plus minus p minus divided by sine theta, which we already worked out. So again, we need to work out what is p plus and minus. So of course, p plus is 853 divided by 1,000. So that's going to be, of course, 0.853. And minus is going to be the remaining amount. So we can also work this out just by doing 1 minus 0.853. Okay, so that's going to be 0.147. So we can work out what this thing here is. So we take the inverse cos of p plus, which is 0.853, minus 0.147, and we need to divide by sine of whatever we got here, which was 1.87, and that gives 0.74 radians approximately. Okay, so just from these kinds of counts, we can work out exactly what the state is. Okay, so I think that wraps it up for today. And so, as usual, please go through the homework for this week. And if you have any questions about that, then we can talk about it during our regular Zoom sessions. So, okay, so thanks for listening and see you later.